In this video, you are going to learn about graphing rational functions. Fortunately, it's not so difficult. It's essentially just combining the knowledge that you learned about polynomials in the last section of the course with what you learned about graphing so far in this section of the course. And let me start by just talking a little bit about a rational function. Now, you might think that a rational function is a function that is purely logical. It always makes the best decisions. It doesn't act on impulse or emotional mood swings or anything like that. But actually, a rational function is not the same thing as a rational person. A rational function actually comes from the word ratio. So a function is a rational if it's essentially a ratio of polynomials. So this is an example of a rational function. This is also an example of a rational function, 1 plus the square root of x, because that can actually be expressed as a ratio of 1 over the square root of x to 1. So just putting 1 in the denominator. So here is a rational function. This is a simple polynomial, like the polynomials that I introduced in the previous section. So this would be a degree 2 polynomial. And you might recognize already the form. So it's minus x squared. So x squared generally looks like a bowl, and then minus x squared, which means it's a bowl opening down. And in fact, the plot looks something like this. And then the 2 here is basically just shifting this whole function up on the y-axis here. So the way to plot a rational function in Python using Matplotlib is essentially by generating a couple of points in the function and then evaluating those points and drawing a line between them. So it would look like this. And in fact, I'm going to start by generating exactly that same plot that I showed in the slides. So let's see, we are definitely going to need NumPy and Matplotlib in this video. So I'm going to specify the x-axis is going to go from -3 to +3, which means I have to specify this as 4. And then I'm going to run this first example generating this function point by point. So what I need to do first is initialize the vector of y points. So I'll say numpy.zeros, and that's going to be length of x. So before actually moving forward, let me show you what x and y are. So here's x, that's a range from -3 to +3, and then we add 1 here. And then y is a bunch of zeros, and it's the same size, or it has the same number of zeros as the length of x. Okay, and so what I'm going to do now is loop through all of the values of x in this range, and then replace each of these zeros with the actual value of the function at that point of x. So for I in range 0 to the length of x, we say that the ith element in y is equal to basically the function definition. So 2 minus x, and then it's the ith element of x squared. Okay, and then we are going to plot this. So plt.plot x by y, and I will make this squares with lines connecting the squares. All right, so there you go. That looks like a nice plot. Now you could embellish this a little bit more. You could spend some time making this plot look a bit nicer. You could draw some grid lines, some x and y axis labels, and so on. By this point in the course, you know enough to be able to beautify this plot a bit on your own. Instead, I would like to move on and show you a little bit more about plotting functions. And in particular, the next thing I would like to discuss is the resolution here, or the number of points that are on this graph. So let's plot another function. How about y equals 2 plus the square root of x? Actually, the square root of the absolute value of x. So it's a bit similar to a function that we plotted in one of the previous videos. Okay, now notice that I'm actually specifying the entire function on one line here. So this is different from evaluating the function one point at a time. Now there isn't really a general reason to prefer one method over the other method. In certain circumstances, you will find that it's useful to generate functions one point at a time, and other cases it's useful to specify the function all at once. So I'm going to say that x equals, and now I would like to basically change the resolution of these dots. So x is going to go from -3 to +3, but I want to be able to specify how many points there are between -3 and +3. And to do this, I'm going to use a function in the NumPy module called linspace. And the way that the linspace function works is that you provide 3 inputs. The first input is the lower bound, the second input is the upper bound, and the third input is the number of steps between -3 and +3. So let me print this out so you can see what this will look like. So you can see that we have numbers from -3 going up to +3, and now there are 10 of them, so I can make this be 20 numbers between -3 and +3, and so on. So now that I have this specified, I'm going to make a plot of this function. So plot x by y, and let's also make this squares with lines, but I think I'm going to say M for magenta. All right, so this looks pretty interesting. This is our plot of the square root of the absolute value of x. So it kind of comes down and then it's flat at the bottom and then it goes back up. Now what would happen if we changed the axis limits a bit? So for example, if we would make this plot generate from -3 to +4. So now we actually don't get that flat plateau at the bottom. Now it just comes down to a point. Now maybe there's something about the resolution. So what if we were to say, how about 14? So now, you know, the plot generally has this same form, but when I change these parameters, in particular when I change the resolution of x, it kind of seems like in the middle it's changing a little bit. The function seems to be changing a little bit. And actually what's happening here is that this plot is not really showing the function itself. Instead, it's showing just a collection of data points evaluated somewhere on that function. So therefore, these straight lines in between them are a little bit misleading because it suggests that the function actually is straight from one point to the next point. Now, as long as the points are sufficiently close together, that's not really a problem. And in fact, you will learn later on in this course that linear functions, which is essentially what we're doing here, are actually really good approximations of nonlinear functions, which is what this is, as long as the linear spacing is close enough. So we can make this even higher resolution. And now this line, this estimate of the function, the square root of the absolute value of x, starts to look more and more like the real function. And also, by the way, the more points we add, the more kind of annoying it looks with these squares. So maybe it's better if we remove this s and just leave this as a magenta line. Now, I would like to take a moment here before the exercise to illustrate to you one of the things that I love about exploring mathematics with tools like Python or other numerical processing softwares. If you would see this function here and you wanted to know a little bit more about this function, and all you had at your disposal was a piece of paper and a pencil, it would basically take you a really long time to try and get more familiar with this function. But in Python, it's really easy. For example, if you want to know what does this function look like if you subtract the square root, super easy. All you have to do is change this line of code, or even just this one character, and then you get to see that this starts to look, I don't know, like the roof of a house or something. Maybe you're curious what happens if you say 2 times x minus the square root of the absolute value of x. And then it looks even more interesting. Or what if we would say 2 plus, how about instead of the square root of x, we would make this be the cube root of x, so to the power of 1/3. Okay, well that one actually doesn't look so different. Oh, but maybe we can do something like this. Maybe I can say y1 and then y2, and that will equal the square root of the absolute value of x. And now I can say y1 and y2, and we'll make y2 be a black line. So this is pretty interesting now. You can see parts of the function look really similar, and there's only one piece of the function that I'm changing, and you get to see how changing the fractional power of this function will change the resulting graph. And that right there is the most powerful way to use Python to help you get an intuitive feel for mathematics. And with that concept in mind, your goal for this exercise is to produce a plot that looks like this. I think this looks really neat. This almost looks like it could be an icon for some hip software company or something. So essentially, this is a similar set of functions. It's all y equals x to the power of something, and that something goes from -1, 0, 1, 2, and 3. So pause the video, switch to Python, and see if you can produce a plot that looks like this. Of course, I recommend running through this in a for loop to make this efficient. All right, so let's see. The x-axis was numbers that went from -4 to +4, and I don't really know what was the resolution that I showed in the slide. So I'm going to start it off with, let's say, just 10 points for starters, and maybe I will need to increase that later. Okay, so then we're going to have the exponents, and I'll just call that E for exponents, and that's going to be in a range from -1, and in the plot I went up to, 4, up to the third power, so here I write 4. Okay, so now we're going to have a for loop, and this will say for I in E. This is pretty compact coding here. So let's specify that the function is x to the power of I, and then we plot this function, so x comma y, and then we need a label, and that label was y equals x to the power of, and then I'll do a %s in here, and then a %i out here. All right, and then we need to activate the legend, so plot.legend, and actually no, before going much further, I think it's a good idea just to look at this plot and see how it looks. Okay, so it's getting there. Let's see, there's a few things that we need to fix here. One is that the lines need to be a little bit thicker, so I'm going to set line width to be equal to 4. And now I want to adjust the x and y limits, so let's set the x limit to be set according to this x limit here. And so that's going to be the first element of x, so the first value of x, and then the last value of x. All right, so this is getting somewhere. It still doesn't quite look like the figure that I showed in the slides, but we're getting closer. I'm also going to set the y limit, and let's say, this is getting a little bit out of hand here. I'll say -20 to +20. So -20 to +20. All right, so this looks a little too rugged here. So I think what we need to do is increase the spacing between -4 and +4. So how about instead of 10, we try 100? Aha, this looks much better. And now I'm curious to see if it gets any better or different if I set this to be 1,000. It doesn't really look much different. I wonder if I can just set it to maybe 200. Yeah. So you can see at some point you get up to the resolution that is sufficient, and then adding more data points is basically just going to make the computation take longer without really adding any new information. Okay, so this generally looks pretty good. The last thing I want to do is convert this into LaTeX so it looks a little bit nicer. In particular, I want these exponents to be in the superscript. So here, when you are using LaTeX in a label for a legend or in a title, you can actually just encase everything in $signs like this, and that means that we use the LaTeX code for superscription, which is the caret symbol. All right, so now this looks quite good. So what a fun video this was, wasn't it? I hope you enjoyed it as much or maybe even more than I did. So I told you about rational functions and a little bit more about plotting, but I hope that the most important take-home message for you from this video was how to interact with Python and how to change functions so that by visualizing functions and changing the arithmetic of functions, you get a better feel for the underlying mathematics.